Greetings to all and welcome to this lecture. We are in module 3, which is two terminal mass structure, and we are discussing the region of operation. So this is lecture 3, region of operation, inversion 2. In this lecture we will explore and get much more insight into the strong inversion and the inversion, or the classification of the inversion region, be it in weak inversion, moderate inversion and strong inversion. We will see what is the definition or the extraction method of threshold voltage. To be precise, extrapolated threshold voltage by extracting from charge versus voltage graph. These are the learning outcomes of this lecture, which helps you to explain the characteristic of strong inversion in a MOS capacitor. It also helps you to understand the inversion charge and the potential relation. Let's do a quick recap. In last lecture, we have discussed about few of the approximation to simplify our mathematical framework. So we said that instead of calculating the inversion charge by some numerical integration and consider the thickness of inversion layer varies from y surface to yc with a delta y thickness, the overall charge can be calculated as y surface to yc minus of q times ny dy. Instead of using this approach, we concluded that the other approach to calculate qb dash is much more simpler. We considered depletion approximation, which says that the entire depletion region is made up of immobile charge carriers only, and hence there is no mobile carriers available into it. The second, we considered that the charge sheet approximation, meaning the layer thickness of inversion charge is negligible, and hence the voltage drop across this inversion layer thickness approaches 0. So all the potential will drop across the depletion thickness. We also calculated the depletion thickness, which is nothing but dB is equals to square root of 2 into epsilon s divided by q into Na into square root of psi s. Here psi s is a surface potential, epsilon s is the permittivity of silicon or semiconductor, Na is the body doping. We have seen that by using this approximation we can calculate the inversion charge like qc dash minus qb dash. By using a good amount of approximation, we can write qc dash from our general equation of qc dash as minus signum of psi s square root of 2 into q into Na into epsilon s into psi s plus e to the power of minus 2 phi e to the power of psi s minus 2 phi f over phi t into phi t. This was the total charge equation, and hence we did some approximation and calculated qb dash. By doing so, we have extracted qi dash. Based on that analysis, we said that the inversion can be classified in 3 parts like weak inversion, moderate inversion and strong inversion. The onset of weak inversion was at psi s is equals to phi f. The upper limit of the weak inversion was defined by psi s is equals to 2 phi f, and the strong inversion will occur beyond that value. Much more about how the charge varies with the surface potential. So this is the total charge per unit area, which includes your qc dash, qi dash and qb dash. Here we are plotting the magnitude of the charge, though these charges are negative, but we are only plotting the magnitude of the charge with respect to surface potential. So when the surface potential is increasing beyond 0 and it will be less than phi f, ultimately you are in depletion. So the depletion charge qb dash was given by minus of 2 into q into Na into epsilon s square root of psi s. So ultimately the inversion charge or the bulk charge was directly proportional to square root of psi s, and hence we got this curve, which simply says that the charge was given by immobile ions. Now if you increase the voltage, the surface potential increases, and even beyond the phi f, the majorly charge governed by the depletion charge only. There are some amount of mobile charge carrier presents, but we will neglect, and this is considered as onset of weak inversion. Till 2,5f, if you see, the overall charge is captured by QB dash only, and hence you will get almost a linear graph or quadratic or dependence of square root times of psi s graph, which says that this charge is captured by QB dash only. Here it is not necessary only to see what amount of charge we have, rather how the charge is dependent on the change in the potential. If you see carefully, to change the charge in the depletion region or in weak inversion region, we need to apply significant amount of change in surface potential. It means you need to increase the voltage, gate to body voltage, in such a way that there should be a significant change in surface potential. We termed it as psi s1. So corresponding to delta psi s1, the change in the charge is only delta QB dash, which is nothing but the total channel charge. However, after 2,5f, due to the exponential dependency, this inversion charge is taking off and it is exponentially rising, but this exponential rise will not happen exactly at 2,5f. It occurs after 2,5f, and hence we cannot say what is the exact onset point of strong inversion. That is what we classified these regions as moderate inversion and strong inversion. So there is a region comes into picture where there are some mobile charge carriers available into the surface and the immobile charges are also there, but your surface is not fully inverted or not having a huge amount of inversion layer thickness. So that is called a moderate inversion. So in general, we will take the onset of strong inversion as psi s is equals to 2,5f plus a new quantity phi z0. Here the phi z0 is some multiplier of phi t. So let us say I am taking a capital N, where capital N can be 5 or 6. It depends upon the substrate doping and the oxide thickness. It means what amount of voltage you should require to causes a strong inversion, it depends upon the body properties or the substrate properties. So in general, we consider the surface potential or the onset of strong inversion is 2,5f plus phi z0. Now what will happen? The total charge, if you see in this region below 2,5f, where you are talking about weak inversion and depletion, the total channel charge is actually governed by QB dash only, and we ignored the QI dash. However, beyond that point, the significance of QI dash comes into picture. So this graph is actually the total charge, which is nothing but QC dash is equals to QI dash plus QB dash. If we see the relative change in the surface potential here, in strong inversion, you change a surface potential with very small amount, it causes a significant change in the inversion charge. So delta psi s2 is very small than delta psi s1, which simply says that we have seen how the surface potential varies with VGB. So if we plot a surface potential till 5f to 5f, then this is almost linear with a constant slope, and beyond that point what will happen? It will drop to a smaller slope. Then what will happen? This region of operation is termed as 2,5f plus phi z0. So this is 2,5f line and this is 5f. This is a strong inversion region. In the strong inversion region, the change in the surface potential is very small, however change in the charge is very large. That is what we have seen from our previous analysis, that after 2,5f there is an exponential dependence of QC dash on psi s. So this point is 2,5f. Now can we derive an alternative form to relate the gate to body voltage with the channel charge? In precise with the inversion charge, which is QI dash. So again we can use our basic understanding of potential balance equation and charge balance equation to derive a alternative form. So let's start with potential balance equation, which says that VGB is equals to phi ms plus psi s plus psi ox. Now here psi s can be replaced as phi ms plus psi s plus qg dash divided by cox dash. So psi s can be replaced by qg dash by cox dash. This can be written as phi ms plus psi s minus q naught dash by cox dash minus qc dash by cox dash. We have already did this kind of exercise. This quantity is nothing but a flat band voltage plus psi s minus. Now here this qc dash can be represented in terms of qi dash plus qb dash. So I can rewrite as qi dash by cox dash minus qb dash by cox dash. If I want to rewrite this equation in terms of inversion charge, then qi dash can be rewritten as minus of cox dash, which is a slope of line between qc dash and psi s. It can be written as VGB minus of V flat band voltage minus of psi s minus of gamma into root psi s. How this term comes in? Because qb dash was given by this equation. So qb dash was square root of 2 into q into Na into epsilon s square root of psi s. Now when you take cox common, ultimately the cox will come in denominator and this quantity becomes gamma. So you have a closed form equation which relates the surface potential psi s, VGB and inversion charge. If I want to rewrite this equation in terms of what is the amount of gate voltage is required to cause the inversion, or you can say like this, what is the amount of gate voltage is required to cause what amount of charge above the surface potential value 2 phi f. So if we plot the surface potential versus VGB graph, then what we saw is this graph is almost linear in the weak inversion. After weak inversion the slope is decreases. So can I get some value of VGB which helps me to determine that this VGB values is for weak inversion, this VGB value is for moderate inversion, and so on and so forth. So can I define the value of VGB which decides the onset of weak inversion, moderate inversion and strong inversion. So corresponding to the surface potential, if owing to this linear dependency of the slope, we can get this value VLO is onset of weak inversion, VMO is defined as onset of moderate inversion, and VHO is defined as onset of strong inversion. So to get this value of VGB, we need to rewrite this equation, the earlier equation what we derived in terms of Qi dash is equals to minus Cox dash VGB minus V flat band voltage minus psi s minus gamma root psi s in terms of VGB, which will give you this equation. So ultimately VGB can be given as V flat band voltage plus surface potential plus gamma times of this parameter, which includes the significance of both depletion charge and the electrons. Now can we calculate this value VLO and VMO or VHO? So for VLO the surface potential is phi f. So I will go back here and I will put surface potential is phi f. So V flat band voltage plus phi f plus gamma times of this is phi f, however this will become what, e to the power of minus phi f over phi t, which is very small quantity, though the surface potential is positive, but it is smaller and hence this quantity will be smaller. You can simply neglect this quantity to get a simple closed form equation of VLO. So VLO is that gate voltage corresponding to which the surface potential is phi f. Similarly, we can put 2 phi f here and we can extract the value of VMO. So VMO is the gate voltage value corresponding to which my surface potential is 2 phi f. Now if I am interested in VHO, then I can put the surface potential value as 2 phi f plus phi z0. The calculation of phi z0 is not that easy because it varies with substrate, right, with the substrate properties like substrate doping and the oxide thickness. So, phi z0 can be represented as n times of phi t. For uniform substrates, this n lies between 5 to 6. So, it can be phi z0 can be written as 5 times of phi t or 6 times of phi t, where phi t is nothing but what, kT over q, which is 26 millielectron volt or 26 volts, because you are actually representing in volts. Now, if we relate the previous graphs which were actually plotted between surface potential and the mod of total charge and the surface potential and the applied voltage, this will give you a complete solution, because the ultimate goal is how my surface potential react with applied gate voltage and correspondingly how my surface charge respond to this surface potential. So, if we plot side by side, it will be easy to understand the significance of each parameters. Here we have plotted VGB. So, we are actually changing the VGB value or increasing the VGB value in such a way that at VLO the surface potential is what, phi f, at VMO the surface potential is what, 2 phi f. So, this is onset of weak inversion, this is the upper limit of weak inversion. If we see, the weak inversion can be defined as the slope delta psi s by delta Vg B is almost constant. So, the weak inversion can be defined by the slope of surface potential versus VGB graph. After VMO point, what will happen? The strong inversion takes place, but we cannot fix the value of VH0. What I just mentioned, that it depends upon phi z0 value, but the surface potential pinning starts. The surface potential will just get to a fixed value. Now, if we see this implication here into the surface charge plot, then we will find in the weak inversion the charge is predominantly governed by QB dash, which means that the depletion charge, we do have some amount of mobile charge carriers, but the significance of that mobile charge carriers can be neglected in weak inversion. However, when we talk about the MOSFET, that this amount of charge carrier is a very important concern when we will talk about subthreshold slope and we will talk about subthreshold conduction and all. As of now, if we see in weak inversion, the charge is much more captured by QB dash, but the moment you crosses the surface potential after 2 phi f and reaches into the strong inversion, this inversion charge dominates, and hence the total charge can be given by QI dash plus QB dash. Now, how can you classify what is inversion? To classify the inversion, we will see that the graph between QI and the surface potential is almost linear. So, you can see from this graph here, the QI dash and VGB graph is almost linear. So, you have two classification. One tells you that weak inversion is classified that the surface potential and VGB graph is almost linear, and one when charge versus VGB or charge versus psi s graph is almost linear. So, this is strong inversion and this is weak inversion. Now, let us get some insight into the value of phi z0. As we said that the phi z0 is some n times of phi t. It means exactly at 2 phi f the charges is not exponentially rising. Exactly at this there will be a charge, but after this point it is exponential rise, and hence inversion charge rises up. But the bad practice is we can take this value as 2 phi f only. So, for psi s is equals to 2 phi f, the bad choice, though it is a bad choice, but historically we can use psi s is equals to 2 phi f and we say that the surface is inverted. However, to solve this and get a precise extrapolated threshold value, what we considered that you have a surface potential of phi naught whose value is greater than 2 phi f by some amount. by delta phi, or you can consider it as a phi z0 also, nothing changed in that. So ultimately you have some surface potential which actually increases the depletion region, and beyond that maximum depletion region the inversion start. So we can again rewrite those equations where we actually said that when your MOS structure is like this and you are applying a gate voltage, so the gate voltage value VGB is such a way that the surface potential here reaches to 2 phi f plus some delta phi. That delta phi amount is actually causes much more depletion, and hence you will attain a maximum depletion width, and that's what we are saying dB max. So the maximum depletion width corresponding to what? Phi naught, where phi naught is nothing but 2 phi f plus phi z0 or delta phi f. At this depletion thickness you can extrapolate you can get the bulk charge, which is nothing but square root of 2 into q into Na into epsilon s root psi s. Now in that condition the psi s has become what? Phi naught. Now again by using the previous equation, which we called it as qi dash is equals to minus of cox dash VGB minus V flat band voltage minus psi s minus gamma root psi s. Here the surface potential is nothing but phi naught, which is 2 phi f plus phi z0. So you can rewrite this equation as cox dash into VGB minus V flat band voltage minus phi naught minus gamma root phi naught. This quantity can be replaced as VT naught. This is called extrapolated threshold voltage, right? So VT naught can be given by V flat band voltage plus psi naught plus gamma root psi naught. This is same as what we have extracted VLO and VMO values. So you can simply say VT naught is the amount of gate to body voltage at which the strong inversion just starts or strong inversion occur. Now the question is, how can I fix this VT naught? Again we have already discussed that keeping VT naught same as VM naught, it means VT naught is equals to VM naught, tells me the surface potential is what? Exactly 2 phi f. It is a bad choice, meaning when in older days when the supply of the MOS structures or MOSFETs was very high, almost 5 volts and all, right, 5 volts, 10 volts, in that condition if you measure this small change of millivolts, right, this is not significant. However, in recent era, when you are talking about low power devices, when your supply voltage is maximum of 1 volts, 0.8 volts and so, in that comparison to 800 millivolts, the change in this millivolt is significant, and hence you need to choose this VT naught precisely. Now how can you choose this VT naught? Again we can say that in the strong inversion my slope of Qi dash and VGB is almost linear. So what we'll do, we'll just draw a tangent and point or get an extrapolated value of VT naught. That is what VT naught is not taken as surface potential psi s is equals to 2 phi f, rather psi s is equals to 2 phi f plus some amount. The better approach to find out this VT naught is to calculate the slope, because if you see this slope of this graph between Qi dash and VGB is very gradual. At this stage the slope is almost linear, but in this in between this is very gradual, right. One may calculate VT naught by using approximation with acceptable error. In this context, the acceptable error is also defined as what application you are looking for. For example, if this is the inversion charge value and you say I can tolerate the 10% acceptable error, then you can simply choose the value of threshold voltage VT naught which is close to VM naught, because whether you take this value of charge or you take this value of charge, it does not matter, because you accepted that error can be 10%. But if you want to model a particular device which says that acceptable error range is less than 2%, it means you have to choose this value of gate voltage at which the inversion just starts, or you will enter into the strong inversion close to this value VHO. It is not close to VT naught, and hence this value will give me this charge is in acceptable range of 2%, and hence you define a new parameter VH naught, which is the value of gate voltage which will give you the strong inversion. So again, VH naught can be defined as V flat band voltage plus psi s plus gamma root psi s, where psi s is even greater than 2 phi f plus phi z 0, because the acceptable error range or tolerance is less than 2%. So this is the approach to find out the values of VLO, VMO, VT naught, which is nothing but a gate voltage value which tells you in which region of operation your MOSFET is working. So let me summarize. In this lecture, we have discussed that the channel charge is smaller in weak inversion, in the sense the total channel charge is predominantly governed by QB dash. Though in weak inversion a few amount of inversion electrons are there, mobile electrons are there, but we considered that it is dominated by QB dash. We have also seen the values of gate voltage, which is defined as VLO, VMO, VHO. These are the onset values, onset of weak inversion, onset of moderate inversion, and onset of strong inversion, corresponding to which the surface potential is phi f, 2 phi f, and 2 phi f plus phi z 0, and even more. Accordingly, we said that how we can classify the weak inversion and strong inversion. In weak inversion, the slope of psi s versus VGB is almost constant or linear, and in strong inversion the slope of inversion charge versus VGB is almost constant. So we will stop here for today. Until then, take care.